All right, welcome everyone. Can you hear me?
Yes.
Good. All right. I will welcome to this Innovation Summit on Life Technical. I'm really eager to hear a lot about that. First, I would like to, after welcoming you, say that I'm here together with a few of my colleagues, or all the colleagues, Erik, Lars, and Elida in the back. Elida is you are, and also Jonas in the back. And Malin should be here. Oh, she's probably downstairs. They're all participating in the project in different percentages. But Elida, you are broadcasting this.
Yes.
That's really nice. But so if anyone has an issue with that, or maybe a part of your presentation, some of your challenges or something like that, is secret, please say so, and then we mute Elida. And
not mute me, mute the camera.
All right, but a few words on about the Materials Business Center. The reason for our existence are those two facilities, MAX IV. You will hear more from Magnus about that later on, he says. I won't go into any details, but you know of them. Excellent materials research facilities. But as hosts for those facilities, we now have the best of possibilities to make something more out of this, to create an environment where you not as a researcher only comes for a day or two to perform your excellent research, to create an environment in which you want to stay and build your business, because here is the best environment where you have open doors to expertise and experience and business support. But also an environment for established companies, because here you solve your materials related challenges. That's what we want to contribute to the Material Business Center, to build this environment. And we in practicality we do it mainly through a few activities. The one is building bottom up a community of the materials startups and give them the very best support we can within the frameworks of the Swedish law. And then for you established companies that are here, we are trying to collect your challenges and canalize them to the right problem solver, whether it's a startup or it's the stars at the universities. And then also we want to stimulate the growing or the upcoming of more CROs, contract research organizations, companies that can help you that don't have the in-house competence or time or whatever to perform materials analysis and so on. And mainly we do that by offering their services to our startups and funded by us. Historically, these summits have been triggers for new collaborations and ideas and business and so on. So please make the best out of this day. After each presentation we will have time for questions and we will also have time for coffee and mingle. So talk to meet interesting people. And with those words I will hand over to today's moderator. We're doing this in a new way. We're using Torbjörn from Gränges as moderator, and you are Vice President of Technology and Business Development at Gränges. And you've been there, I checked your LinkedIn, for more than 4 years, and prior to that, you worked at a Chinese steel manufacturer for a really long time.
Not steel.
Aluminium. Sorry. Okay, but with maybe you want to fill in something. Okay, welcome up. And applause.
Pleasure to be here today at this Lightweight Metallic Summit. We contacted Lars and Carl quite some time ago, and we discussed this event here today, and I thought it would be very interesting to set up this kind of summit. We expanded we had a little bit more of a narrow scope first, but then we expanded this into this lightweight metallic, which I think is an interesting topics. It's also very nice to be here in Lund. I have been here before several times, worked with, for instance, Ideon. I'm not sure what people's Chalmers or KTH or think about Lund as a material center, but with the facilities we have here in Lund, I think there is kind of exciting possibilities for the future, that's for sure. I would like to fill in a little bit of from where Carl was ending. My name is Torbjörn Sternsjö, and I have many years in Gränges, actually even 25 years. However, a little bit about Gränges first. It's a typical Swedish material company, material with a very long history, actually established 1896. And there was a period when Gränges was half of the value of the stock market in Sweden. It's during the 1930s or 50s or whatever it was. But the recent decades it was in a way going in the other direction. A little bit of this kind of traditional things happened. We were owned by Electrolux for some time. Maybe some of you know that. Then we changed name to Sapa, which maybe is familiar for some of you, Aluminium Profiles. And 5 years ago, the name appeared again, Gränges. So now we are actually a public listed company in Stockholm Stock Exchange. And we are independent. Basically. The focus we have is on aluminium and rolled aluminium. I will talk a little bit more about that later on. My role then in Gränges is technology business development. I've been working quite many years in China. I was actually in China for 17 years. It's a long time. I saw this development of not only the aluminium industry, but the material industry. Such a fantastic period really China has been going through. But a couple of years ago, 3 years ago, I came back to Sweden, which was a little bit of a challenge in a way, being in China for so many years. That's a little bit about myself. So once again, I'm very happy that we have this summit today and welcome all of you. So I think all then we can go for the first presentation. So let me introduce Dmytro Orlov, Professor of Material Engineering in Lund University, and I think we will talk about lightweighting to improve the structural efficiency.
Yes, thank you very much, Torbjörn.
Yeah, thank you.
I'm also kind of new to Sweden. I arrived to Sweden about 5 years ago. I myself is from Ukraine, and I spent around 6 years in Japan and some time in Australia and moved around a little bit. And one of the biggest discovery for me, is it okay to speak without Magnus?
No.
Yeah. Yes. Okay. Then one of the biggest discoveries for me when I moved to Sweden was when you say metal, people understand steel. So that was kind of a challenge, especially when your passion is around magnesium. I came across this metal about 10, maybe 12 years ago, and I found it so exciting. As some people then, I'm involved quite heavily in material society in the States, and working in the light metal division committee, and people from Hydra in there, who were chairing committee at the time, and I was chairing magnesium committee. They came to present us with some ingredients and so forth, and then people in aluminum business say magnesium is absolutely great metal, especially as a alloying element for aluminum. So, but the true story is, this is true that magnesium is used quite heavily in steel business, it is used quite heavily in aluminum business. But there was a surge of interest to magnesium in late 90s and let's say recent years with the development of raw magnesium alloy grades. So in the past it used to be grades. So then the regrowth of interest to magnesium emerged with development of broad grades, and then further on magnesium was again rediscovered as a fantastic metal for biomedical applications. So what I'm going to talk about is a little bit about lightweighting of magnesium and our contribution in improving the structural efficiency of magnesium. And then mention a little bit biomedical magnesium alloys, which I think was always quite interesting. So there is no time to speak in detail, so I'll try to just touch up on it. And in a very unlikely case, we still have time at the end of the presentation, I will mention other directions of our research, which is equally applicable to many metals, not magnesium only, that's some including steels and additive manufacturing. All right, that's how magnesium arrived to our lives. It is exciting, and first applications of magnesium was fireworks in China. And this perception is still in the business that magnesium is very dangerous and it is ignitable metal. That is true, but modern alloys, it's not anymore if you don't want that. Right? So it was first a bit of historical reference. 1755 was first discovered, and then 1808 was first isolated as a standalone material. Why it is beautiful for the business, in general, it has excellent stability. So I have an example of that from Ford. They make huge advantage of that property. So basically at the casting temperature, it is much thinner than aluminum, so you can make thin walled products quite easily with magnesium compared to steel or aluminum. Then it has easily formed at high temperatures, although it is known to have very limited ductility. With high temperature, it is still excellent to do that. Then machining, which is, better than aluminum, or easier, let's say, not better, easier a little bit to machine than aluminum. It has its own issues, but weldability is still there as well, especially restrictions to welding. It's a really good technology for welding. And as I mentioned already, in the modern alloys, it is not flammable if you don't want that. Then when it comes to abundancy, magnesium is very abundant. It is fourth most common metal on Earth, behind just iron, oxygen, and silicon. Right, then the most abundant is dissolved seawater, so we do have lots of resources. Even in our body, I think most of us have at least 35 grams. It is essential iron element in the body. Then it is larger structural metal, which is just a quarter of that in steel and 2/3 of aluminium, 1/3 of titanium. And it is fully recyclable, which is important in the modern view and the awareness about ecological impact. What is really interesting is about lightness and puzzling is that in 2016, when the list of critical materials for Europe was compiled, magnesium was on the list as one of the most critical materials for Europe. The reason for that is not really the existence of magnesium as such, but the cost of technology, the cost of manufacturing. The reason this list is compiled based on the supply of sources, not only about abundancy. And as you see, this is just one of the recent figures. China dominates the market of primary magnesium. What happens in Europe is we buy primary magnesium and we process and alloy it, but 85% was the figure for 2016. In the last couple of years, basically over the past 10 years, it has been balancing between 80 and 90, sometimes even 95%. The only reason for that is the cost. But new technologies have emerged. It used to be a pigeon process, which was very dirty. At the stage of using magnesium, it is fantastic. At the stage of manufacturing, CO2 emission were enormous, and China at the time did not care about CO2 emissions, so they used that in bulk. So now they have developed much better technologies, reduced CO2 emissions. They have themselves developed much stricter regulations on that. But on top of that, in Europe, we do have resources. We have dolomites here in Skåne. Sweden does have a lot of resources for that. And in Finland, the mining companies that mine nickel and copper, they have around 40% in stock water from the mines. They're striving for companies who would help them to recover magnesium from there. Steel manufacturing, you can recover a lot of magnesium oxide from there. So it's just a matter of developing proper technology for having it here. I would like to encourage this business as well. I think we're ready for that. But then again, magnesium, it is being used more and more in aerospace and mining and marine sectors, and in the still in consumer electronics, you have light devices, especially laptops as a chassis. It is more common to use it in there. Right? So lightweighting in mobility, just wanted to show this figure. Something we very much modern, right? With the petrol and fuel. And then another picture, which was Volkswagen in motion from 1962. I love in general Volkswagen is extremely creative team in promoting, and they were first introducing this Beetle model. In 1962 it was, and that is fantastic, I really love it. So apart from all the beauties of having it when you move the car, so no matter what the propulsion is, if the car is, or the vehicle is lighter, it is easier to move it. And then this is fantastic if you get stuck somewhere in the woods. For Sweden this is very important, especially if you're up north. It is easy. One more important thing which comes in here is the targets. Well, the recent administration in the States has slightly different opinion, but targets, at least these targets cannot change. So for light duty vehicles, so these targets were set in 2015, they're still in there, but just I want to pay attention to the aggressive figures for 2050, when the total vehicle should be 50% lighter what it is. The thing is, which we are stacking into the car these days with electrification, is they become much heavier, because you take out steel and you put in copper to make it work in electricity and electric batteries. So, but you save weight on the body quite a lot, so it is 65% can be saved in body because of the use of light metals. In this business, Aluminium did a fantastic job. They pushed hard steel business, and that's what at least Ford came up with for body in white for aluminum, and their magnesium response was that. Again, it was Volkswagen, actually 1939 for the Beetle. Okay, a little bit more modern example, the research center, Hillman's Centrum Eastart, which they call MAGIC, Magnesium Innovation Center. It is the biggest research center on magnesium outside of China, and they came up with BNDF government-supported project when they developed new grade of magnesium alloys as a sheet metal and the technology for its manufacturing. And if you have Porsche GT3 from 2015 or on, so it has magnesium roof. Then further actual serious applications in more affordable cars, like Renault, EOLab, they have magnesium roof as well. Then Chinese manufacturers, they put luggage retainers in the car bodies, and then magnesium in general as a cast form, it comes and goes all the time. But in the sheet metal form, it has kind of new applications. There is a secret that Tesla also has magnesium in quite a large quantity, particularly as luggage retainers as well. They don't talk too much about that, but they try, they're very secretive as a company in general. So it is opening up. Bosco invested heavily and they developed technology with Samsung on the thin roll casting of magnesium. The volumes are far from those in steel and substantially less than aluminum, but the targets and technology is there. It's just a matter of market uptake, and it is uptaking magnesium as a long-term investment, so it takes some time. And companies invest heavily now in aluminum, steel, new grades of steel, which is another story. All right, so just to give an example, apart from the apparent lightness of magnesium, another good property is the stability. And this is an example from Ford, where steering wheel core was originally produced from 5 pieces of steel, which you need to cast, then the machine, and then you bolt it in. And when they managed to use magnesium for that purpose, it is just 50% less weight. But the major improvement in cost efficiency actually came from the absence of necessity to assemble. So they could cast a single piece, which was impossible with steel, but became possible with magnesium. And then Hydra, for instance, being an aluminum company, they invest heavily in magnesium technology. And so there is a couple big American companies that invest in magnesium, being aluminum primarily. Right, then energy saving, low density, high strength, and these are just the figures for fuel saving, again, important. In this case, it is combustion engines, but still it is it falls for electric vehicles. Then acceptable price for magnesium. When we compare it to steel, okay, steel and aluminum are the benchmarks that are going to be used in the automotive industry. So steel normally would now be the target material cost somewhere between $1 and $2 in the final products, and aluminum is between 4.25 and 1, if I'm right, please correct me. And then if magnesium is to replace steel, the cost of it must be somewhere in the margin between $6.5 and $8 to $2 against steel, and if aluminum components are to be replaced, somewhere between 6.5 and 7.5. So the current market price for primary magnesium used to be between $3 and $4, and in 2016, 2015, end of 2015, 2016, it was 2.1 as a primary. Again, it is sourced from China. So it is profitable. Some other reasons are behind accepting it in the automotive sector, but that's a different story. Big deal was development of sheet metal technology for car body applications. And these are the diagram compiled for POSCO. They investigate steel company invested heavily in magnesium technology. And they compiled these sheets, so depending on thickness and the width of the sheet metal, they're actually the best to build technology for twin-roll casting and then rolling of magnesium sheet metal. They are now stepping back a little bit because of market is not really, the capacities are more than the market demand right now in the car industry. So then there is a push from VOLVO probably is necessary to make it work in some other bigger companies. But Volkswagen is investing quite heavily. They're actually developing competing technology to POSCO, and they're already installing these in the premium cars, the next generation of Passat. Right? In aviation, it used to be banned. In World War II, it was American, some famous planes that were 95% built of magnesium, and but it was still banned from civil aviation up until 2015. And the Magnesium Electron, which is the biggest magnesium supplier in Western countries, they developed, they were heavily pushing it. And in 2015, American Aviation Agency, FAA, they have lifted the ban from using magnesium alloys. So provided 5 safety tests are passed, you can actually, magnesium can be used in civil aviation these days. So highway is open there. There's magnesium hydrogen storage capacity. This diagram shows the efficiency of energy storage per kilogram or per liter of fuel and the price efficiency with gray bars. So if you look at it here, so the hydrogen storage capacity of magnesium as hydride is pretty nice compared to all other diesel or methanol or even high power battery, and especially when you look at the cost, it is much more efficient than the battery. There are some issues, it is not as bright as you want it to be, of course, but the potential is there and it is quite enormous. Body applications, structural metal applications in human body. As I said, magnesium is bioresorbable metal. If you look at this table here, so magnesium, if you compare it to natural gold properties and all the modern alloys, metallic materials that are used in this business, magnesium has the closest mechanical property to the natural bond. On top of that, it is perfectly biocompatible. It is not toxic. There is no issues, for example, as cobalt chromium alloys or stainless steel where you have vanadium or chromium. It is bioresorbable by body fluids. So it is absolutely a fantastic metal to use as a bioresorbable implant. When, unlike titanium, for instance, if you have temporary implant, you put it in the body once, and then it gets dissolved by the time the bone gets healed. You don't need to have second surgical invasion. Beautiful. There is a couple issues. It is resorbable too quickly, so we need to control the rate of corrosion or degradation, and we need to improve structural efficiency. So we are working in these directions. We are working on the development of magnesium alloys, tailoring the technology, improving structural efficiency, and looking into the degradation, which is probably the major issue right now in magnesium alloys. That is something which we developed recently, I think. 3 minutes to finish off with that. That's exactly what we're going to do now. So that is extrusion technology. When you have a round bar, in this case it was 70 millimeter, and then in one go, we have a conical die, and then it goes with this bend channel, with a parallel channel extrusion. right? Then we accumulate much larger strength in our material. What we have after the processing of such a bar, and we managed to produce 4 meter long bars in one go. Then from the initial material condition, which was just a hot extruded state, we got improvement of both strength and ductility because of controlling 2 main parameters. Sorry, one indicational slide about magnesium. So unlike copper or steel or aluminum, magnesium has so-called hexagonal fluorspar lattice, and the strength of magnesium is controlled by plastic deformation on this sleeve on this basal plane and so-called twinning. The combination of these two systems, if you look at the critical resolved stress necessary to initiate plastic deformation in your material, they're working in a parallel and they're quite soft. So basically the structural efficiency improvement can come by restricting these plastic deformation on these directions. And this can be achieved by controlling the orientation of these blocks and controlling the sleeve itself by some precipitation hardening. Couple slides on that. So in the material which we processed, we call it SPD processing, right? What we've done here, these 4 figures, they show orientation of unit cells of magnesium. And what we've shown here is just we randomize the microstructure of magnesium alloy, and by that we activate multiple deformation mechanisms in it, which improves the strength of the material and isotropy of it. And if this is the unit cell of magnesium, typically in AZ and AM series magnesium alloys that are aluminum zinc and aluminum manganese alloys that are typical cast grades of magnesium, the precipitates are usually in basal plane, and ZK series, which is zinc zirconium alloys, they will look like this. And they're not efficient for improving the strength, absolutely. And these alloys, they typically have WE series, where is it? Yeah, WE series alloys. These are alloys containing rare earth. They're more structurally efficient. So they have precipitates in this position, which is quite difficult to develop. What we've done with this ZK60 alloy, which is zinc zirconium alloy without rare earth, we developed this type of precipitates. We discovered that in our alloy, when we do the processing which we could do, in general, zinc is precursor for such features in the microstructure. What we found with transmission electron microscopy in the lab, that we can develop this type of precipitates there right here, like this, that are more common for rare earth containing alloys. We found it in a system without such. So we don't need to compete, for example, with electronics. Then we found with the synchrotron-based techniques like small angle scattering, they actually statistically we do have plenty of them. So they are a significant fraction or contributor to the strength of your materials. Then we did some, again, I think it is marked. So then it was X-ray imaging where we demonstrated that the morphology can be changed. In this case, it is Petra-free, not quite Max IV, but Max IV at the time did not exist with its imaging capacity. Now, Max IV is actually fantastic for working with light metals because the beam quality and the energy range is really great for revealing different features and analyzing it really nicely. Then the main strength of Max IV is surface science, where photoelectron microscopy is used. And in this case, but just by bombarding photons, you can analyze really early stages of oxidation. Magnesium degradation is a big deal. Everyone is talking about that. In practice, no one knows what's going on the surface. Right? So what we are trying to do is to actually understand what is going on there. Max IV is probably the best facility in the world for doing that. So we do actively involve. What we've done at that time at LIGHTer, Max IV was out at the time. So then you can see how magnesium gets oxidated. It's very interesting how oxygen, when it comes in contact with magnesium, it is creeping inside and then it blows it out from inside. So it is very exciting physics. But then we developed in-house facility for the magnesium oxidation in aqueous environment, and from that we come much closer to real-life applications. In the synchrotron, it is still very much staged experiment. In lab, we have just real-life alloy, real-life fluid, so we can do it in a bulk state, and we can analyze every stage of magnesium corrosion and oxidation. just brief summary, we run out of time. So magnesium alloys appear very attractive, and milestones in certification for biomedical and aeronautic applications in there, automotive is there as well. And we're trying to make our own contribution into improving that. Thank you.
Very interesting presentation.
Thank you. Any questions to the video? Yeah.
What about mining of magnesium? How does that compare to, say, aluminum and iron? Are there any issues with mining?
There is no issues, and Skåne is, in Europe, it's one of the best places for it.
Oh,
You have dolomites, and then you calcinate, and it used to be a very dirty process, as I said. It's pigeon. We need chlorines, and yeah, it wasn't as nice. But there are modern technology with electrolytical methods that can allow that to be a lot more sustainable with no CO2 emission effectively. So usually you mine it as magnesium oxide, right? It's like milky water. You can buy it actually in a pharmacy. It's massive relaxant. So, and then you need to reduce it. Yeah, and chemical methods are available there. It's interesting that, for example, Becker uses magnesium oxide in their heating technology. So magnesium, you do not really have to use magnesium as a metal. You can use magnesium oxide. And then there are some technologies now for storing excess heat when magnesium oxidation and hydroxylation. So these are two reactions. Normally magnesium oxide is not stable in the atmosphere, so it hydroxylates. And while doing that, it generates heat in quite substantial quantity. So, but if you heat it up again, these reactions get reversed. So one of the ideas for utilizing excess heat is to use magnesium hydroxide. When you have excess heat, you restore magnesium to magnesium oxide, magnesium hydroxide. You make oxide, and then you can release it by converting back into magnesium hydroxide. So that is alternative use.
Thank you.
Yeah.
Are there any plants in Europe that produce magnesium sheet?
There are big manufacturing in this business. This major Magnesium Innovation Center, which I mentioned, they have perhaps the best facility right now. So they had a fire, which was irrelevant to magnesium. It was just electronics. That was funny, because in their workshop, they had twin-wall caster. And then it was fire in the workshop, but electronics burned out, magnesium didn't. So they were very happy about that. But now they have rebuilt facility, and now they're in the hot stage of commissioning twin-wall caster. And they have this twin-wall casting. Then in Austria there are some investments in this business, and they are working, this Magnesium Innovation Center, they work actively with Volkswagen. Volkswagen is building its own line. And then they are probably buying something from Posca. So maybe more, I don't know exactly yet, but it might happen that the Posca twin-wall caster will actually end up in Europe.
So how is it done? Is it pivots or glue in Scotland?
Yeah, that's a very good question. One of the major problems in utilizing magnesium in car business is galvanic corrosion. So when you make a coupling, electrochemical exchange between magnesium and steel, then that is the weakest spot. So you need to, usually it is bolting with very good insulation, electrochemical insulation from other body components. With the roof, they found a welding technology, but then they were quite hard in getting the connection right. There are some weak spots, but at least Porsche has managed to do it efficiently, to manage it.
It's not only electric coating and painting, different temperatures.
Plasma oxidation is for biomedical application, you cannot coat it with anything. You want to achieve bulk corrosion and well controlled at even rate. But in the car industry, there are some efficient coating. Again, there is one of the groups in Magnesium Innovation Center. They work on efficient coating. They develop kind of active coating that have been shown to be very efficient. Then there is plasma oxidation, which is these days quite commonly used in magnesium chassis for electronics. So there is a couple of technologies that allow. Then you oxidate, you produce oxide with very thick oxide on the surface, which does not oxidize in a way similar to aluminum. Like magnesium just oxide, it is soluble in water, MgO, unlike aluminum oxide. So normally it doesn't stay there. But with plasma oxidation, you make it very dense and non-soluble. Then it works excellent as oxide protection.
Okay, I think that's. Thank you very much, and thank you.
Thank you.
Presentation. So maybe let's continue in the next presentation, which will be my presentation. So, always preparing. I will talk a little bit about Gränges to start with, and also challenges and opportunities with aluminium. I think we can there, yeah. Yeah. So, let me first introduce a little bit about Gränges as a group, and then I will talk a little bit more about aluminium, specifically, not magnesium this time, and about the challenges and opportunities related to aluminium. So, as I said, Gränges is a public listed group. We have a revenue of 40 billion Swedish krona, and we are located globally. I will show that in a short minute. And we have, for quite many years, been focusing on a specific type of material. Racing material for introducing for heat efficiency, especially in the automotive industry. So we have location production in Sweden. Finspång, south of Stockholm. We are located in China, Shanghai, and we also have a production location in US, especially in Tennessee. Last week we actually announced also a position of a big roll aluminum company in Poland. We're very happy to get on board really. So these are our products. Once again, we are producing flat rolled aluminium products. So it's aluminium, rolling aluminium process basically. And the material we are producing is specific material for the automotive industry, also for stationary heat exchangers. And we have a couple of other specific niche markets. In Europe and in Asia, we are 100%. This is the type of material we are using. It's a kind of clad material, a sandwich type of material, where you have a core alloy and you have a so-called film metal. I will explain very shortly here about the basic process. And then you also have another layer on the other side, second type of liner, which you normally have, for instance, in tubes when you have and so on. You see the kind of the heat exchanger there and different components. So it's heat exchanger consists of tubes and films and so on. Really. So this is the type of process that our customers is using. It's a welding process basically. It's called brazing. So what is happening is that you have this clad material. You can see it on the down here, to the right. You have the core alloy, you have the film metal, and you have secondary liner as well as the thick material. So what's happening is that you are heating this up in a furnace basically. And then you get the joining process at the temperature here up to 580 something. And then you get to 600, and then you get this kind of blend formation. So the beauty here is that with the film metal is silicon, so it has a lower melting temperature compared with the core metal. And that's why you get this kind of blending. So this is something that the automotive industry has been using, the brazing technology, for quite many years. around 30 years ago, copper was used in heat exchangers to price and the weight. Then aluminium was basically penetrating this market. And today, I would say more or less 100% of all heat exchangers you use in the automotive industry, trucks also, is of aluminium and using this type of racing sheet material. So a little bit about challenges and opportunities for aluminium. And once again, Gränges has been, I would say for 30 years, been focusing on this kind of racing sheet material. We have not really been into other type of material. Today, you see more and more aluminium in the automotive applications. Dmytro showed this before here, magnesium. And you can see that more and more of aluminium is used in the automotive. The advantage then with aluminium is the lightweight. So starting a little bit from above, what we see from Gränges side, where we have kind of challenges in the future, there's a lot of things happening right now. It's urbanization, driving, of course, transportation, vehicles, and so on. Digitalization is an important trend as well, and the last one, I think many industrial companies now are really putting focus on this. As mentioned about Dmytro about the recyclability, to show a little bit more about that. But sustainability, recyclability is a term that is becoming a very big thing here for the future, really, for the interior industry. So, I think you will know this, that there is more and more of the pressure of the emission of dioxide here. That we can read about it all the time, basically. And what's happening is, of course, that the pressure is increasing on the industry to reduce the emissions. And here I think the automotive industry has challenges, of course. You can see this in this slide when the target levels of emission is increasing continuously, I would say, which puts, of course, the pressure on the manufacturers to reduce the weight. That's why the interest now for aluminium is there. Magnesium also coming up as an alternative material. It's a kind of exciting period coming up right now also. I think we want to talk more about that later on here for the automotive industry. And of course, big challenges as well to meet these emissions. And of course, do it in the industrial scale. That's the kind of trick here as well. Really challenge, I would say, for the industry. From Gränges side, we are affected also. If you're just talking about heat exchangers, which is our core product, definitely these are two big drivers for us. I mean, energy efficiency, yet also in that field is very important. So it's of course, if you're talking then about electrification, you have less of energy. There is the combustion engines, you generate less heat, so you have to solve that kind of problem from a thermal management point of view, really, which is a challenge. Carbon emission, I'm already talking about. So when you're designing this thermal management system, as we are focusing on from Gränges side, of course, you have to consider these kind of things really. And of course, it affects the heat exchangers, and it affects the material requirements of the material as well. Really. Cost efficiency is another thing. I think it's a little bit of a perfect storm right now when we talk about the automotive industry, which we are very much supplying to, I would say, Gränges. Right now, especially when we have a slowdown in the automotive demand, especially in Asia, but also in Europe, at the same time we have the requirements of emission, we have the change of powertrain, which is a very big thing, really. So I would say right now the whole industry is more or less, I would say, almost stopping up the development of material or components for the ICE, thermal combustion engines, all R&D, all development cost is very much put into the electrification and new type of powertrains. I think Johan can mention this, but a little bit from a general point of view, that's very clear. Really. That's something which is happening right now. The other thing is, of course, the development is fast. It's uncertainty in terms of technology as well. Take, for instance, thermal management for electrification. You can see on the market right now a lot of different technologies used for solving that kind of specific issue, which is, of course, a challenge because we all know that this industry is a matter of scale, it's a matter of volumes, and all these different type of technologies cannot survive there. So that's of course a big challenge here. With small volumes and uncertainty is what is becoming the kind of the winning technology moving forward here. So it's definitely a very, very interesting period, also affecting the material industry very much in this industry. So this shows a little bit how we are working with our customers, and as I said, for the 30 years we have been into this industry, it has very much been a matter of weight. So I would say that the heat exchange as such, if you take just a simple radiator, maybe I can say that the size of it and the weight has reduced by half over these decades really. And right now we see that this is more or less stopping up when it comes to heat exchange for the ICE. Focuses more on the heat exchange used for the electrification. This is the kind of thing we are working when we are how to say developing material for our customers. Of course, we're getting conceptual targets, gauge and yield strengths, and the target is many times to reduce the weight and of course also the cost. I think this kind of development here process, this is very typical of automotive. One challenge with the material industry when we talk about developing new material, new applications, is actually the lead time, and it is the validation period. Here, I think for the material industry, there are definitely an interesting period as well, coming up new technologies like artificial intelligence and so on. We can start to see that it's coming into the material industry. Can you use that type of technology to speed up, shorten the lead time, which is of course a tremendous importance when we talk about new material technologies and new possibilities, especially in this kind of period we are right now. As I said, for us the focus is very much on electrification. We have to derive a new type of material we have developed quite recently. For the treatment, I'll briefly explain that. In this racing process, you are using kind of fluxes to remove oxidation on the layers. For the treatment material, we have included, actually incorporated this flux salt into the aluminium metal. Flux salt is potassium and fluoride salt, which then is from the beginning, which gives advantages to our customers. So right now we are really working in close cooperation with our customers to develop the new applications, like for instance battery cooling plates, which is a big new application coming out for EV. And also I would point out this importance for the material industry to work in partnership here with customers, but also with other partners. I think that's something you can see quite becoming more and more common due to the situation. This is, of course, also from an industrial perspective extremely important when you are into mass production, especially in an industry like automotive. Everything is about consistency, everything is about to retain the same product quality. from a material engineering point of view, it's many times interesting and exciting to talk about the most optimum type of material. But the fact is that the consistency in product quality is actually more important, really, because that is a must in order to reduce the cost, which is what everything is about in this type of industry. Really. I think that's kind of very important also in academia, that always have this in mind, that it's not always the most optimum material solution which is the winning technology. It's in fact from a total cost perspective, and this is very much a driving force for the total cost. To have a consistent process, to have a consistency in the product quality. That's still a must, and it will be there also for new powertrain and electrification. Right. Gränges is active in something called the World Material Forum. It's a French initiative focusing on the material industry's role in the new world of importance of sustainability. And being in the material industry, I think sustainability is becoming critical. The fact that the resources are limited. We talked about recyclability before running out of magnesium. I think all the companies in the materials are trying to promote now their material based upon recyclability. And we hear it more and more. But the fact is that this is becoming very critical. I think also here Johan probably fill into this. We have this saying here in the World Material Forum: use smarter, less and longer to develop a KPI system. So our CEO is active in this organization. And I think those is smarter, less and longer is kind of good buzzword. Describes quite well what this is about. This is definitely a very important area. This is also something I think most of you heard about as a multi-material solution. Once again, I'm not an expert in this area, but the fact is that the trend is slowly moving into more different type of material in the automotive. What is really deciding this development? What is deciding if you're using aluminium or steel? I think that's a question which I would like to address to you probably later on here. But yeah, I agree. Very much a cost, and interesting to see that different than manufacturers, different OEMs or in the automotive are using different solutions already. I guess it depends how you calculate them, probably. But anyway, you can see here that there are the important thing I think here is the fact that everybody believes that we have the multi-material solutions in transportation vehicles coming up with. I think all materials have a possibility to enter in here with the different advantages. And of course, if you can, it's a matter of combining these type of different materials to find the optimal solution. And there you have probably different formulas, different equations, different manufacturers. But that's in a way the general trend. Of course, traditional steel is reducing here the portion, but the steel industry is anyway developing new alloys from the aluminium industry. We're facing the challenge. We are fighting very much with the steel industry here, and we see that the development, for instance, from 5,000 alloys more into 6,000, and in the future become more of 7,000 alloys moving forward. That kind of trend you can see in it. You have also from non-metallic material, composite material, which I think also is becoming. There's a lot of discussion around this cost as a disadvantage when it comes to especially composite material. But if that industry can solve that, then of course you have a quite interesting possibility for that type of material. I'll show a couple of opportunities here from lightweight metallics. I will not have no time to go into the details, but just kind of showing you that what we and also in Gränges looking a little bit on where can we see the future development. AEM at manufacturing process technology, extremely exciting of course. We see some real development. Has been an industry which has been very much on the hype curve, but going down and probably now going up a little bit step by step here. Bigger and bigger interest. And the fact is that we see that there are possibilities, for instance, even for aluminium in that type of some aluminium powder for aluminium. Composite, already mentioned, and you can also here think about combining composite with aluminium, for instance, as a layers of aluminium and composite together. That exists. Once again, here the process in this process cost is the die casting old technology, but also there we are interested in this. See opportunities. I think they're related to, for instance, electrification, components, new requirements, but also the fact that we can use more of the recycled materials, which is important. Graphene, more of a, I will not explore or talk more about that, but the fact that if you can manage to get using graphene into, for instance, aluminium, then you can see kind of interesting opportunities in that type of material. So to incorporate graphene into aluminium would be quite very interesting new options. And the last two here, metal matrix composite, that's actually what I talked about before. In our example, one parts of an aluminium foam finally, something which has been the kind of development stage for quite some time. It's not been any breakthrough consistency here for but there are properties to this opportunities. So in a way, in the interesting period, a lot of new possibilities for aluminium and aluminium applications, I would say. So, for us, how we are looking on the future global trends, of course, what's happening in the automotive electrification is kind of exciting, I would say. Same time, very challenging. Sustainable solution, I would like to stress on that again. We in the industry are talking a lot of efforts into this right now. Actually, company like Gränges, it's so important since we have many investors who really want to know exactly how we are working with that operation. We have to really show that we're making progress in this area, which is kind of interesting. And you know perfectly well that it's not only property also, we actually talk about how successful and how much are we driving. Energy efficiency, lightweight material solutions, and also using utilization, artificial intelligence for material uses, right? Moving forward. So this was a little bit about my presentation. Sure if you have any question?
Yeah, I have a question.
Okay.
You mentioned the perfect storm, and this is the case. There's a lot of things going on. Heat management systems for electric trucks in some cases, of course, a big deal. You need to also think about living and working with that, with food and user, with solutions to this big system. What you didn't mention was inside. And that is something that will require a lot of because it's not so radiators as we have it today is not enough. We require much more. Something maybe that or things to investigate.
I actually have a few. No, you're right. And I think you know more about fuses than I do. But you're right that there is a high requirement on cooling. And we have been working on actually one in Gothenburg. I think you know that company. Power cell. And we have been. I think that's interesting technology really. And I'm not present in China here also. It's a kind of more and more interesting industries. There are specific companies like Toyota driving this. Hyundai is also in truck industry. Is generally interested in and once again, I can say that of course there are technology challenges with this, and I think the key here in order to meet these challenges is probably a cross-functional partnership to develop solutions. I would say from material industry to the use of the fuel cell and also for OEMs side, try to develop this as quickly as possible. I think the old way of working in the automotive industry has it's that kind of system is established of really taking out as much cost as possible, meeting the quality requirements, but maybe the automotive industry is not used right now to work with this high speed, find solutions for meeting all these kind of new requirements, and especially the cost side, I would say, which we all know is the biggest pressure they have. I'm not sure if I'm answering your question, but I agree that it's an interesting technology. Okay. One more? Yes. No.
You also see applications for aluminum in battery cells. The weight contribution to the battery
I'm not completely expert in that field. They have one guy who is sitting in the board of Gränges. His name is Peter Carlson, the founder of Northport. He should be here and answer your question. But no, but I think right now you are using aluminium actually in the lithium-ion batteries. So you're using on the cathode, you're actually using a cathode form. So you have different materials in the cathode. But in the cathode you are using aluminium and aluminium foil as material. We are actually Gränges is looking into that possibility. Quite many aluminium producers right now is interested in this. You see the tremendous big volume demand for growth in this area. So that's one product. You are actually using also for battery casings. So if you take prismatic cells, you have a battery casing around the cell, which is using aluminium. So there are usage of aluminium in the different iron battery cells. And then you have the new cell technologies coming up for the future. That I cannot really answer the question. Okay. So, I think you will call.
Yes, let's see if Eva-Lis is here. Yes, you did it right. Okay, so are you ready to present?
I have my presentation on use.
Let's go for it. Eva-Lis from RISE and we talk about light or challenge. That's the partner. Sorry.
My name is Eva-Lis Odenberger, and I work as a researcher at Louis in Houston. And I'm here instead of Cecilia Wahlberg, which is the director of LIGHTer. It's the LIGHTer arena in Sweden where industry and academia work together in lighting technology. So I will start to give just a brief presentation of LIGHTer and then also give some research examples which we work with at the E.E.Technical. So what is LIGHTer? First of all, it's a network, as I mentioned, where companies and the academia can collaborate together in new lighting technologies. They have the strategic innovation program, SIP Lightweight, where they can have funding for development and research projects from Vinnova. And they also have a membership program. You can see some industries and universities here that are connected to LIGHTer. So it's over 400 unique organizations that have participated until now. So it's mainly all the big industries in Sweden and also a lot of small and medium-sized enterprises. And the motivation for LIGHTer is, of course, the environmental challenge that we all face. We have legislations and also goals that the industry has to fulfill. We want to create competitiveness for the industry and also increase the innovation efficiency in Sweden. So that's the main three motivations. And there is also a LIGHTer agenda which is continuously updated. You can find on the web for LIGHTer. And LIGHTer also work with different programs. One is the development projects part, where you can apply for funding and conduct different development projects in different industry segments. And the goal here is that different industry segments should collaborate to take larger technology steps. They organize workshops and seminars, a few every year. They have the LIGHTer Academy. It's 13 excellent researchers that get funding from LIGHTer to do cross-sectional research activities. We have the LIGHTer PhD network, and it's over 80 PhD students from around Swedish universities that work with lightweight technology in different aspects. We have industrial application, also regional nodes that work with lightweight in a specific way connected to their regional business area and competence. They also have a program for SMEs, and they also have a test bed which is called LIGHTest. As I mentioned, there are 13 researchers from 5 universities that work in specific projects, but they also work together to increase the cross-sectional research activities. And the PhD network is it's more like we have a PhD course where we involve 5 industries in Sweden. It's TK and aerospace, VOLVO cars, Bartek, Saab in Linköping, and Dia in Holland. So the students get to do industry visits, and they also have theoretical lectures. And it's hosted by Lund University of Technology in cooperation with KTH and Chalmers. They also have workshop seminars, about 8 every year, in different topics. Since 2014, there are 90 industrial development projects that has been funded for the Swedish industry, and about 30 SME projects. And within there, they have a specific call about twice every year where small and medium-sized companies can apply for funding for studies that they normally don't have the possibility to perform on their own, and then they can collaborate with researchers from institutes and universities. Light test is a test bed. It has one node in Lund and one node in Piteå. And there has been so far 13 pilot projects. And so the idea here is to propose one offer for the industry where they can test new ideas and new concepts. So we have a lot of test facilities that can be made available to the industry in different ways. LIGHTer also have a newsletter which you can subscribe at the LIGHTer.SC. It comes every month and we have a lot of information on what's going on with LIGHTer. Also LIGHTer organized the LIGHTer International Conference. It was now in Gothenburg this November. Next time it will be in 2021, so it's every other year. And it's a meeting point for LIGHTer technology and innovation here in Sweden. There are many interesting presentations and time to meet. They also have a workshop part where you can network and discuss future ideas. Any questions on LIGHTer? Feel free to interrupt if you have any questions. And, so I will also give some examples of what we do at WISE, EVF in Lund. As I mentioned, we also are part of the light test bed. And so I have some materials from myself and Lluis Carroll. He had his dissertation last Friday at the University of Technology. And also young Alexis, which he mostly worked with composite materials and joining technologies. And our group also focuses a lot on metals, shell construction, so it's sheet metal. And since we have also VOLVO cars in Olofström, we are focusing a lot on sheet metal forming and different aspects when it comes to tool and die design and friction properties, and also a lot of material testing to characterize material properties. So I will take some examples from Lluis' dissertation. It was myself and Mats Odenberger, which is a professor at Lund University of Technology, who has been his supervisors. And it's a LIGHTer project in connection to GK and aerospace. And Lluis has also been one of the PhD students within PhD network. And it concerns different aspects of modeling, computer calculations on how to form and weld aerospace components in an effective way. And the focus is GKN's lightweight products that they develop. So we really have 3 different projects which was funded from Vinnova. And it's within NFFT, so it's the National Aerospace Program, M.Sc program. And also now we have a project funded by LIGHTer, where we will look into hot forming procedures of a lightweight component with discontinuous sheet thickness in nickel-based superalloys in this case. So the motivation to this project is for GKN to manufacture continuously lighter aero engine components, which has a higher efficiency and where you can reduce the amount of greenhouse gas emissions. And they are focusing on a fabrication method where they can use different alloys and material forms such as sheet metals, castings and forgings, which they weld together into complete engine structures. And by that they can combine the best possible material properties and minimize the weight of the component. And the challenge here in this project was to be able to predict the accumulative shape distortions which take place in the forming, welding and heat treatment procedures. and to be able to compensate those using finite element model computer simulations. And by that, contribute to minimize costly compensations and tryouts that they face in the pre-production phase or in the development phase. So here is a knowledge gap from how the industry works today. For example, we see that we have to use the history from the code of hot forming procedure as an input to the welding simulation or heat treatment simulation in order to have very high accurate simulations that you can use to have a trial and error process in the computer environment instead of doing a lot of testing and modifications in the pre-production phase. There are also a gap of knowledge when it comes to predicting cracks during forming in these materials. And if we can have high accuracy in these simulations, as I mentioned, we can also compensate the forming tooling not only for the spring back after forming but also for welding deformations. So I will give some examples here. So in our lab we work a lot with material characterization methods where we can test the material properties at high temperatures, from room temperature up to over 1000 degrees C. And we work with tensile tests, we have biaxial tests, and we have different types of shear tests where we can study damage and failure properties in materials. And here are some examples where we use digital image correlation. We have a stochastic pattern, and then we can have a very high resolution of the strain measurements and study in detail when the crack appears. And these type of tests generate input for the mathematical models in the computer simulations. So here is an example of a yield surface, which determine if the material is loaded elastically or plastically. So we study a lot of specifically anisotropic material properties where the material have different properties in different directions in the material. So we can feed the models with all the input that we give them at different temperatures and different strain rates and loading directions. So in Lluis' work we started with curve forming simulations and testing to produce outer case geometry, which is a commercially interested component for Liaison. And we have problems predicting the failure that could occur, but by using a model for failure and damage we could be able to see actually the crack and the gap in the simulation. And it's an important part because if you can predict when the material starts to fail, then you can change the process so you can fully use the material in that room. We also extracted a part from the formed geometry and performed welding tests. So here we have the residual stress state after forming, and then we did simulations of the welding procedure. Here you can see the temperature increasing as the ready torch moves over the part. And here you can see how the residual stress state changes, and of course it introduced shape deformations in the part. So we have worked with both simulations but also produced forming tools, welding fixtures, and measuring the shape deviation compared with simulations. Also, we work with hot forming, and this is because materials are very expensive, so we want to avoid having expensive materials. So we heat up the material with a target temperature of 950 degrees centigrade. In this case, these are very temperature stable materials because the working temperature in the engine is at about 650 degrees. So it's very resistant to temperature, so we have to heat them up at a very high temperature. And we can use the properties in the material where the stresses relax with time. So we consider the time and temperature dependent properties in order to relax the stresses and thereby reduce the amount of spring back. Because if we will have a crash forming procedure in room temperature, it's very high strength material, so it will just spring back. We will end up with no deformation or geometry at all. But by using hot forming, we can produce parts much cheaper and faster than if we use a cold forming procedure. So in this case, we have also done simulations where we don't include stress relaxation, and in that case we have about 10 millimeters of shape deformation, which is out of tolerance for the industry. If we include the stress relaxation, we are at the shape deviation approximately 1 millimeter, and it's within the tolerance that the industry put on the part. So, we also work with other materials, for example aluminium or titanium, and also different high strength steels. And here is also a project with GKN where we study forming and additive manufacturing. So here we have a sheet metal part which has an AM reinforcement in order to make the part more structural, high strength part, and up to a minimum weight. So here we have had, for example, a master thesis here in Lund at University studying material properties. And we also work with medium-sized enterprises. In this case, it's Lydrak and Institute. And we also work with Malm, which is here in Skåne. And in this case, we also work with hot forming. In this case, we have formed at about 700 degrees centigrade. And by developing this process, we have been able to cut the cycle time almost 10 times compared to the production that takes place in the US today. And it is by using modeling that we can have a trial and error process. We can test which type of forming temperature do we need, how long does the holding time has to be for the material to relax. We can also compensate for spring back, and that I reduce the time. So in this case, we have done a pre-forming on the line. And the next stage, we do simulations of welding, not AM in this process, in this project, but we will also look into modeling of additive manufacturing. So GKN has done welded reinforcement on the pre-formed line, and they also has built with the AM process. And the last step here is to do the hot forming simulations of this reinforced part. And in this case, it's Lydrak that helps us to produce the two components. The last example is a hybrid hood put together with VOLVO cars. It's an aluminum hood where they study to decrease weight by adding reinforcement in carbon fiber. And as you see, we have also different types of companies, material suppliers, also tool coating companies that have expertise in tool coatings. And we also have sub-suppliers for VOLVO cars that are involved here because they see that future lightweight components maybe not are only metal, it could be combinations, hybrids of metals and composites. So here are a lot of activities going on, and when it comes to the test bed facilities, we have forming tools, different types of forming tools designed to easily change the inserts for different geometries. So in this case, they do the forming and curing in the tool, so it's heated up to about 200 degrees centigrade. And they have tried both SMC and also mixed fibers. So here is the tool frame, which can be used for many different geometries. So it's quite cheap and fast to study different types of parts, different types of materials for different customers. And here is the produced part. They have also started to put in fasteners, elements for joining in the same procedure, because then you could reduce one production step. You could form and insert joining elements in the same process. And of course, we have research activities also concerning modeling, because it's quite challenging to model forming in composites and the curing process. So some examples on what we work with in Liaison and also about LIGHTer. Thank you very much.
Questions? Yes?
I have a question about Nickel 718. You use superalloy state valid LIGHTer platform.
Yes.
What is the context for using?
Because it's a high strength material. And for example, in the aerospace industry, you have to have metal that can sustain very high running temperatures. And then you became limited to which type of materials you can use. And we study also new types of nickel-based superalloys, for example, Haynes 282, from which you can reach and increase the running temperature by approximately 100 degrees centigrade. And then you can increase the efficiency in the engine, reducing carbon dioxide emissions. And using simulations, you can also study which type of thickness do you have to have on your component. So you try to optimize it, optimize it, both with strength and weight. So even if it's a high density material, it's a high strength material, and it's still for lightweight components. So TKN's target is they have to reduce the engine weight with 500% every 10 years in order to meet the legislations. Was it answered?
Yeah, that is the link. The reducing the weight of engine, right?
Yeah.
Any other question?
Are you studying inclusion of graphene as
Well, graphene is a very interesting material, so I think there are some discussions about how to use it maybe as coatings, but it's really on a quite deep research level at the moment. I think graphene has a lot of opportunities, but it's still maybe in an investigation stage or research stage on how to really use and apply them. We have projects together with Chalmers where they have their graphene flagship and where they do a lot of research. In our test bed, it could maybe be connected to coatings or maybe insulation between different types of materials where we have, for example, corrosion problems or it's nothing that is available now, but it's an interesting field.
Short question. At the end, the composite carbon fiber and aluminium. Do you have any indication of weight savings in percent of, say, aluminium?
I have to get back on that actually because it's Johan and Alexis that are working on that. But I can't say the percentage, but it's a major weight saving actually even from aluminum. So and that's why VOLVO has now had 3 different research projects in this area, studying and combining them. Because I mean it's step-by-step procedure for the industry also to change materials, find material suppliers, look into traceability, reproducibility when it comes to high volume production. So it's many steps that has to be taken. But you can see from their efforts that they are very interested in investigating it, because that is light saving potential.
Thank you, Eva-Lis, and I guess it's 10 minutes.
Yeah.
Coffee break.
Right. Okay. Thank you.
Thank you, everybody.
hålla mikrofonen närmare munnen. Så det hörs ordentligt. Då så. Då efter det där pausen så går vi vidare. Och jag would like to welcome, now I should put English. I would like to welcome Johan Lindqvist from VOLVO Trucks to have a speech about lightweight in commercial vehicles. Very interesting. Welcome, Johan.
Okay, so kind of place
There is in the top. Yeah.
Okay, great. So yes, my name is Johan Lindqvist, and I'm from AB VOLVO in Gothenburg, here in Sweden. Thanks for inviting me to this conference today. I'm working as portfolio manager, responsible for advanced engineering, and my portfolio is basically developing trucks and services for the future. What we do today within my portfolio and other advanced engineering portfolios, you will see on the streets in maybe 5 to 20 years time frame. Today I will talk about something maybe a bit old-fashioned, lightweight and load capacity. I will not talk so much about the perfect storm that we are in. I will come to why. VOLVO Group mission is to drive prosperity through transport solutions. And this is important. It's not only about trucks. We need to optimize the complete logistics in the society. VOLVO Group is big. We employ almost 100,000 people around the world. We have manufacturing facilities in 18 countries, and we sell our products basically everywhere you can go in the world. This is what we do: trucks, buses, construction equipment, and propulsion systems for boats and ships. Just to mention, we don't do cars anymore. VOLVO Cars was sold in the 90s to Ford and is now owned by GE. However, we do share the same name, brand. Talking about brands, in the pictures here, you see a lot of different brands that is a part of the VOLVO Group. And the reason for this is that we need different brand that has their own brand characteristics that is optimized for the different market segments they are sold in. And some here you will recognize, for example, Renault, VOLVO trucks, construction equipment, VOLVO Penta. But we also have, for example, Mack in US. You might be familiar if you have seen the Cars movie. We have different bus brands that is not common here, like Nova Bus. We have Prevost Bus. Construction side, we have SDLG, Terex. And then on the truck side, around from, we have Dongfeng in China, Eicher in India, and UD Trucks in Japan, formerly Nissan Diesel. Last year, we had a total sale of 391 billion SEK, and we are making money. The operating income was 34.5 billion, so almost 10%. Our biggest business is trucks in VOLVO Group, and last year we sold almost 260,000 trucks worldwide. Interesting in this picture that I didn't choose myself, it's from a company presentation. It's this truck you see here. It's called Super Truck. And it's a research project we have been running together with the Department of Energy in the US, basically investigating how far can we reduce CO2 emissions for on-road transport. And it's optimized in many different ways. What's interesting in this forum is the lightweight solutions. We don't see it here, so it's a lot of waste above the chassis here, but under here there's a complete chassis made of aluminium actually. And this project is, I mean, it's government funded partly, and then Volvo funded. So you can actually Google it, Super Truck and Volvo frame, aluminium, or aluminum as they say in the US, if you want more information. I guess many of you don't really think about lightweight seeing this picture. And it's actually a heavy transport. But the thing is, in order to transport this excavator we see at the back here, that is big, probably the truck, the trailer and the excavator have a lot of lightweight solutions to make this transport even possible to do on a public road, to make it street legal. So there's a lot of lightweight solutions in here actually. So, then why would someone buy a truck? Many customers, they love their trucks. But the thing is, we don't sell many trucks because they are cool. A customer usually sees a truck as a money-generating machine, more than something the customer buys to impress the neighbor. So, how do we make this money of a truck? We use a method at Volvo called vehicle lifetime productivity, which is very easy math. The hard thing is to get all these figures. Basically, we add all costs associated with the transport to one bucket. And here is overhead for a company, salaries for drivers, tolls, roads, bridges, etc. Finance, there is the sort of the delta between the purchase and the resale value of the truck, and interest rates. Service is actually a big post. It's not only cost for service we take into account here, it's the downtime. If you have the truck in a workshop, you have a driver with salary that can't do work, the truck is not generating money, and you probably have a contract with someone to deliver something. So you need to handle that in another way, maybe buy and transport someone else. So it's a big cost associated. And fuel. And as a rule of thumb, this will vary a lot, but 1/3 fuel, 1/3 salaries, and 1/3 for the rest for operating the truck. And all these costs must be, I mean, you need revenues that are bigger than the costs to make money. And what is bringing revenues to a truck? Well, it's the cargo. It's what you transport that brings the money. And here the competition is very, very tough out there. So it's very small margins. So how much cargo you can take, the load capacity or the payload, each and every turn is extremely important for the customers. And this is what is used when selling the truck. Of course, revenues should be bigger than cost. This is a picture of a truck as we like to see it, with a trailer doing its work. I mean, a truck without a trailer is waste, so it's probably due to some bad planning somewhere. This is a very common transport in Europe. It's a 4x2 tractor, so this is the tractor, we say. A 4x2 means it has 4 wheels with the traction on the rear ones, and a trailer. This is very common in Europe, since it's legal everywhere. You can drive everywhere with this combination. The trailers are standardized, you can switch them, so it's a complete infrastructure built up around this transport. If we should name one bread and butter for the Volvo group, I would bet on this one. I'm not sure, but I would bet this is the product. All countries around the world have regulations in terms of weight of trucks. So here are some commonly used terms. Front axle and rear axle load. It's basically the weight or the pressure the tires put on the ground, what the sort of asphalt would feel. This is summed up to something called gross vehicle weight. We have the load from the wheels at the back at the bogie and the trailer. And all this is summed up to gross combination weight. So this gross combination weight is actually the weight of this complete truck and trailer. And this is what typically a bridge would feel. If you have 10 trucks meeting at the same time at the bridge, I mean, we need to control this. And for this truck and trailer, it's 40 tons that is allowed in total. I don't have time to do the math here, but this combination actually has an opportunity, we can say. The thing is, when you start putting cargo in the back here, we reach a limit where we actually meet this regulated limit before the combination actually is full. So instead of the maybe 24 tons you should be able to take, you can only take 23.5. So it's half a ton, maybe not so much, but going back and forward every day over the complete lifetime of a truck that is more than 1 million kilometers, this is money for the owner, but it's also a waste of CO2 because the emissions per ton kilometer, as we talk about, will go up. On the positive side, and this is why we actually work with lightweight, there is a leverage included here. You see 1/3 here, so 1/3 of what you put back here actually ends up on the truck and this. So if we can reduce the weight of the truck 1 kilogram, we can actually put 3 kilograms of cargo at the back. So to compensate this half a ton, we just need to reduce 160 kilograms here. So there are examples where it actually really pays off to work with lightweight solutions for the customers. Another example is there's a lot of different regulations. This is an example from Brazil. They only allow 6 tons on the front axle, which is very tough because a truck like this maybe is 9 tons on its own. So on the front axle we basically are at this limit already. So here it gets very, very sensitive when you start putting cargo in the back and you can't really put any load on the front axle. So here we see examples sometimes that if 1 kilogram can be removed on top of the front axle or in front of it, we actually can load 20 kilograms more at the back. And the target is to always have full trucks because this is the most effective. So why do we care about full trucks? This slide was developed by a project that we are running called High Capacity Transport. It's a collaboration between the Swedish government, Finnish government, VOLVO, Scania, forest industry, Kinnarps, and probably some more. And basically we are testing the pros and cons of having bigger, heavier and longer vehicles on the road. And just to cut it short, it's really a success. It's really implemented, already implemented in Finland actually. But in Sweden we're working with it and we're trying to sort of export this idea. Because here they made a calculation example. If we're transporting 200 pallets goods between Malm and Gothenburg with this typically standard transport, we need 6 trucks. The CO2 emissions will be 10 kilograms per pallet. And with these heavier, longer vehicles, we actually only need 3 trucks. And we can reduce CO2 by 30% just by doing this. So this would be perfect application to go between logistics hubs, for example, harbors, and applications like that. For us at VOLVO, however, this maybe is a bad business because instead of 6 trucks, we would sell 3 ones. But taking into account all the need to reduce CO2, we still think this is the way to go. To reduce CO2 by 30% in other ways is very, very hard for on-road transports. If you look at the other scale here, if you make this kind of van transport, there's actually very common. If you go out on the E6 here and have a look yourself, you will see a lot of these kind of transports. And of course, they are very flexible. I mean, B driving license, you don't need to care about working resting hours, but it comes with a cost. Almost 50 kilograms of CO2 per pallet. we will rest our eyes on this one then. The Nordic countries where we have water, I mean the electricity comes from water, etc. Down in Europe, it's a bit more complex actually. But railway is great. We work a lot with these intermodal transport systems. I mean, because if there is a train available, we should use that and take the truck to the railway station. Trains probably are better.
In CO2.
Yeah, in CO2 in many cases, for sure.
But, sorry, but the rumor says that the train is more horrible for the moment, according to the better electricity in Sweden.
It's changing.
Is it?
They're all changing to water.
Okay.
Germany's started it already, and we have a train in England now. All trains and all transport in the future will be run off of the cell, hydrogen cell. Electric is not the future. Batteries are not green. They're stacking up now, and people don't know what to do with it. Hydro cell is the future.
Yes, next slide. This is a truck cab. It's a Volvo FH. It's something we have in production today. We have had it for some years by now. This is our premium truck. And basically, it's what we have. All the yellow stuff here, the members, is made out of high-strength steel. We are using hot form boron steel, the windshield members and the doors, not in the picture here. We also use tailor welded blanks. And all this is joined together with spot welds mainly. Spot welds is great, it's cheap, fast. Laser bracing, rivets, and adhesive bonding. And this, I mean, this cage here is extremely important for the safety of the occupants. A truck doesn't have really the deformation zones that you would see on the passenger car. It has to be very strong. And for example, if you look at the A-pillars here, they need to be very thin because they can't obstruct the view of the driver. But at the same time, it has to support the roof of collapsing in accidents like this. This is a quite common accident type actually with trucks that they go too close to the ditch basically. And at the same time, all the reinforcements that we see in the roof, floor, doors, windshield helps supporting the cab in accidents like this. Or actually, it's more common to turn it around it and we have a truck hitting another trailer from the back in like a queue accident. But it's the same kind of road case. The safety is very important for us. We put a lot of effort into making this work. If there is an accident, people must be protected. So, this is a truck not doing its job, but it's on a racetrack, racing a Koenigsegg for some reason. It's a nice picture, I really like it, speed and everything, but we need to sort of land somewhere, or I need to land. This is a machine, it's not a sports car. In this sort of non-scientific graph here, I will try to explain how we see lightweight solutions for the future. On the y-axis, we have sort of the pros, load capacity potentials. On the x-axis, the cons, high volume in maturity, production investments, part cost penalty, etc., risk. Today, we use a lot of steel. And we're optimizing it, we're using higher strength steels, we use a lot of gray and nodular iron, and it's actually a good reason for it. Steel is very good. It's great actually, it's strong, it's fairly cheap, it has a high modulus E, we can form it, we can weld it, it's easy to repair out in the workshops, and it's also easy to recycle. But it comes with a weight penalty, for sure. We use aluminium today, more on bolt-on parts for the trucks in different areas, cab, chassis, powertrain. tomorrow. I mean, we constantly have an evolution of our products. Each and every time we sort of release a new one, we will have more optimizations, more high-strength steel, more aluminium. Here, I think, on the aluminium side, I think we probably have the big potentials for hang-on parts like doors, hatches for cab, as you see in the car industry, but also if you can replace many of the modular iron big parts we have in suspension systems, etc. We're also starting to use composite hang-on parts, load carrying stuff. In the future, and this is sort of what will change our manufacturing setup. We will use more advanced steels. We will probably use integrated aluminium and body whitening chassis. And I'm terribly sorry, we don't have magnesium on the map, Peter. But maybe it should be here. The thing is, in this area, if you talk about body in white, we actually are fast followers because the car industry are really doing the development for us, and we take solutions from them that is mature. So right now it's aluminium. We probably will see magnesium, sheet metals, etc. in the future. So we are of course looking into that as well. Additive manufacturing is we understand the potentials, but it's hard to really get to manufacturing solution at this point. What we do in this revolution, what we should call it, is that we are benchmarking, not a good color here, I see. We are benchmarking, we are investigating new materials and how to join it. We have to work with manufacturing very closely. Today, our manufacturing is very, let's say, effective. We buy coils of steel, we bring it to a factory, we cut it, stamp it, weld it, paint it, and at the other end we have a complete cab rolled out. And here, I mean, if we are doing this with future material, we have to maintain that because it enables us to lower the cost of our products. But basically what we do, we are building knowledge, and of course these more exotic, high-risk solutions, they probably are not exotic and high risk. They should be more in the standard business. So today I have not talked about the technology revolution or perfect storm that we are facing with a lot of electrical vehicles. I have not talked about automated vehicles. I have not bragged about our 1 million connected vehicles. I'll talk about lightweight. But the thing is, for a truck, if we don't have the load capacity, the customer don't care if it's connected or not. We just must have the load capacity there, otherwise the customers will buy from someone else. So we have to do everything. Thanks.
Any question to Johan? One of the large lorry companies, they're actually working on hydrogen cells. Is it VOLVO or is it Scania? I can't remember.
You said
hydrogen engines that run on water.
Fuel cell or
Yeah.
combustion of hydrogen?
Yeah.
Fuel cell.
Yeah. Someone's working on it. I can't remember who it is. I heard it for the grapevine. Either VOLVO or Scania.
In general, I can answer that. Probably everyone is working on this.
But the trains are there, you know, everybody, the German train now has been running for the last 6 or 7 months. It runs on one full tank of water, 800 kilometres, and it just produces steam. So England took the initiative as well. I thought we were a bit slow because initially we talked about leading it, but we have water trains as well, where all they produce is just steam at the end of the day.
I mean, hydrogen is hydrogen is very promising. I mean, it's like an electric vehicle, but you replace the batteries with the hydrogen basically and the fuel cell. So I mean, it's very promising. I mean, if we have a hydrogen infrastructure, so we can fill the vehicles, it's it can be definitely something.
And it's green as well.
Yeah, definitely. It's a probably good solution. But you have other solutions like biofuels, etc. that work with the stuff we have today.
Biofuels that I don't think are any good at all.
What?
Biofuels are not a future thing. I remember when biofuels come out, I've had some high-powered cars in my time, yeah. And if you can walk around any car park now that all fuels now, Shell, BP, whatever, all had to have so much percentage of biofuel put in the fuel as an additive, yeah. If you remember looking around car parks years ago at height of sports cars, any car really, something that really had a bit of go in it, you look at the exhaust, right? They were grey because the engine was running correctly, grey. Then you rub your finger around them, they're black like chimneys. What is coming out of those can't be good for the atmosphere. Also, I had a big
CO2, it's of course very effective because we're not adding any new CO2 into the environment. But it's many different solutions, and we are everywhere, I can promise you.
I had a big 4x4, yeah, a little bit slow. I had to work on the engine, took the whole engine out, took it around. One of the pipes where the fuel went should have been about, I don't know, inch across, whatever. It was blocked right up, you could just barely get a pencil in it. And that's when they introduced this biofuel. And also, I talked to a Shell driver, a tanker driver, it clogged up all their engines as well. The tankers that were delivering the fuel. So that's biofuel for you.
Okay.
You have one more question back there? You talk about front load and how much you can put on the lower. Is legislation ready for autonomous vehicles because you'll shift the weight balance when you have lesser weight up front?
Yes, yeah, I mean, legislation is ready for autonomous vehicles when they arrive in large numbers, I think that. We also have the sort of battery electric vehicles that are quite heavy, where we also need to review this. But I mean, it's not so easy to change these values for the governments because I mean the complete infrastructures with bridges etc. are designed for it. So it will take time.
Yes. Just material selection solutions. Can you elaborate a bit more? What is critical for you when you make your choices of material for a specific type, and how long your solution works normally? Like, is it 5 years? Is it in light-weighting duties or 10? And what makes you change your solutions that are already implemented?
Well, it's competition mainly, I would say. I mean, it's very, very tight. I mean, the difference between the different truck manufacturers is quite small. So we are constantly sort of raising the level together with other manufacturers. So this is driving, and it's also the profits by the customers. It will be automatic because they will choose the one that gives the most profit, basically. So we have to be on top. So this is what's driving. So we constantly, in all projects we are launching, we have weight targets for the products. And so what we do in advanced engineering is that we are preparing solutions sort of on the shelf. Okay, next big project. Okay, here's a palette of solution.
In your ranking of solutions for a new vehicle, where the light saving on the material weight targets, how far they are from the top? In material selection,
it's different actually. Right now, I mean, Volvo Trucks is very good in terms of load capacity and lightweight. And maybe we focus on other features like safety of the driver, CO2 emissions. So I mean, it will vary in different projects for sure, but it's always a target. Because if you don't have this target, we can be sure it will be heavier. That's all we know, because we are constantly adding features. We're adding higher requirements for after-treatment systems, better sound insulation. The trucks must be for inside, but also for the outside. So there's a lot of challenge all the time. That sort of, it's very easy to buy something and add on the truck that solves the problem. But it will just not work to add stuff all the time without optimizing.
And what is the heaviest component in your truck? Sorry, last question.
The heaviest? Yeah. A good question is probably the chassis with all the wheel suspensions, etc. But I mean, a full cab with the interior is probably 1.5 tons or something like that.
I have a short question.
Yeah.
If I remember correctly, the Swedish truck makers they have 3 tests on the cabs. Lund test on the Lund test on the back, and there's a weight drop test on the roof. Is this the same for all the truck makers in Europe?
Oh, now you're asking tricky questions. I mean, this pendulum test I know was a Swedish test that was tougher than the legislation required. But I think the legislation are changing right now. So, but we have a lot of requirements internally that is above the legislation because we are the VOLVO brand and it's in our DNA to focus on it.
Because the implications are that if you have to sustain higher loads, then the design will be heavier.
Yeah. It will drive weight for sure, and this is the reason why we're constantly adding more hot form boron steel, etc., and making smarter designs.
Okay, thank you. Thank you very much, Johan. Thank you for this. And let's Magnus now, Magnus Larsson. And Magnus will talk about MAX IV, I will believe so. We hope the technology works. Yes. Excellent.
Thank you very much. Okay, let's dive down into advanced materials characterization. And I would like to talk about MAX IV. So my name is Magnus Larsson. I'm head of industrial relations at MAX IV. And I want to say a few things about what is this MAX IV, what's happening here in Lund, and also talk about how do we work, with some examples, and also how do we work with the industry in trying to open up this facility for use of the wider use of the society. So for these advanced new materials that we're developing, we also need new tools to understand them when we're developing them, and a lot of the material properties that are key, they are on the atomic level, on the nanometer level, on the micrometer level. And in order to understand and modify those properties, we need to be able to see them, see what we're doing, and understand what we're doing. And for that and many other reasons, Sweden is investing heavily in advanced research infrastructure. So Sweden is building both MAX IV laboratory and also the ESS, the European Spallation Source. There's no one here speaking about the ESS. I would say a few words about that as well. So what is MAX IV? It's a Swedish national research infrastructure, and it's the Swedish synchrotron light source, and it's funded mainly by Swedish public funding. So we have funding from Vetenskapsrådet, Lund University, Skåne region, and Innova, but also from a lot of universities and the Knut and Alice Wallenberg Foundation put in a substantial amount of money in equipping the facility with the right tools. But we also have some international investments and also some investments from industry through the research community and Novo Nordisk in Denmark. What is MAX IV? You can say that it's a series of advanced X-ray microscopes. So it's different types of analytical tools. They're all based on X-rays. And I'll say a little bit about neutrons later. But an important thing to know is that we are a user facility. So the researchers working at MAX IV, the facility is not built for them and their experiments. It's built for the wider user community. And the usual setup is that a researcher plans an experiment over time and then comes to MAX IV, performs an experiment over a day or a week, and then goes back with a lot of research data to work with and analyze and continue working with. And our main user base is the academic user base. So a lot of PhD students and postdocs and other researchers comes and perform experiments. But we also open in other ways, and I'll show you that later. But we're really a user facility, and we are still in a ramping up phase. We are in operation, but this year we'll have about 1,000 users. When we are fully up and running, it will be something like 2,000 to 3,000 users yearly passing through our facility. But we're not alone up there in the northern parts of Lund. So here's the MAX IV facility. There's a construction site north of us is the European Spallation Source. But there's also this area between the Science Village Scandinavia, which is right now it's a green field, but in the future we hope to see companies, organizations, Lund University and others will move up there with part of their facilities, and also other, of course we hope to see restaurants and other things there as well. We're a little bit alone up there still. We have some food trucks, but other parts will also grow there. And the city of Lund will grow in this direction, and if you've been up there, you see a lot of things are happening in the Odenberger area. And we now have the tram line. It's going to start next year, so it's going to be easy to get up there. So MAX IV and ESS, twins but not identical. So we are both research infrastructures, we are both user facilities with a steady stream of users passing through. But MAX IV, we are working with light, with X-rays to probe matter. We are a Swedish facility and we have a history from here in Lund. There was a MAX I, II, and III before MAX IV. So we have 30 years of history. The old facility was down at the LTH area. It's now decommissioned. We're completely up here at Odenberger. And with X-rays, you can probe the electrons and bonds and get a lot of chemical information. I will dive into that a little bit more, what you can get out with X-rays. But neutrons is what ESS is working with, and it's a European membership project, so 15 states are investing in this. Sweden and Denmark are co-hosting, so the research laboratory is here in Sweden, in Lund, but there's a data center built in Copenhagen, which is another important part of the facility. So it's a construction site, as I said. It's a little bit more now. It's difficult to keep up with new photos there. A lot of things happening now, and in 2023, by the end of 2023, I guess they will start with the first experiment, but then the real user program will start in the years following. And with neutrons, you probe the atomic core, and you can get another set of information out from the material. You can play around with hydrogen deuterium substitution. It's very important for organic matter. You can also probe quite large and thick samples. So thick set of steel, but that's not what we're talking about here. We're talking about lightweight materials, and X-rays are excellent in probing and understanding lightweight materials. So why do we build a facility like this? is because when we make these X-rays, we accelerate electrons. So we have a long tunnel here, 400 meter linear accelerator, where we accelerate electrons and feed them into two storage rings, one with slightly lower energy and one with higher energy electrons. And then we have these sections around the rings where we force these electrons into strong alternating magnetic fields. And when the electrons see that magnetic field, they bend and they lose a little bit of their energy, and that energy is sent out as X-rays. And since we have accelerated the electrons to very close to the speed of light, 4 meters per second slower than the speed of light, we get this fantastic, very focused parallel beam. And that's what we want to have when we probe matter. So when you have a lab X-ray source, you get more light bulb kind of X-rays, but we want this really laser-like. And we have very interesting properties, a lot of photons per square centimeter. We have a very focused and narrow beam, and it has high coherence. It's very laser-like and contains a lot of information, and we can use that to probe matter. And there are a lot of things we can do here. You see, I wrote these little wiggly things because we get the light out as tangents here. So it means we can have, when we're fully up and running with all the stations, we can have 25 or so experimental stations running in parallel, performing all these different experiments all around the clock. And that's also the reason why we do this in circular shape. And why we have two different is because we are interested in having a little bit low energy, and this is where we come from Max Lab and from the Swedish research communities, very strong in different spectroscopic methods to understand really the chemistry, the electrical and magnetic properties of matter. But now we're building this large ring also, and we're opening up for other techniques, more scattering techniques and more imaging techniques. So if you just roughly divide it up, you have all these spectroscopic techniques where we get this information about matter. But also we have these scattering techniques where we can see the atomic level or nanometer level information. And then we can put together our signals into images and get these imaging techniques. And I will see if I can show some of the examples here. Today we have 16 funded beamline projects, and we call them beamlines because we have this beamline, and at the end we set up the experiment. And they all have these interesting names, and they all have different techniques, but they're all X-ray based techniques. And the green ones here you see we have 8 in user operation today, so we're taking users. And we have some of the orange ones, they are in commissioning, and the grey ones are currently being built. And next round that we open in spring here, all these 5 beamlines as a small ring will be in operation, so we'll really be able to serve the Swedish user community in all these spectroscopic techniques. And we are getting online with more and more on the large rings, where we have many of these other techniques. So let's dive down into some of the techniques. We have one beamline called HIPPI. HIPPI, HI stands for high, but it's not really high pressure, it's more ambient pressure. We have the XPS techniques, where we penetrate matter with light, and the photoelectric effect kicks out an electron, and this electron carries a lot of information. And this is an ultra-high vacuum technique, so it's really 10 to the minus 9 or so pressure. But here we are building these ambient pressure cells, so we can bring out the pressure to 100 millibar approximately. And then you can suddenly have a more realistic environment. You can have a liquid film, you can look into more dirty samples, or you can have a gas situation. And here we have an example of Gränges showing here. And we have, when the industry is coming, you can come and pay for your access here. And you can keep everything to yourself and keep it secret, but Gränges, this is from E.E.Technical. So it's like open with that they came here and did some experiments, and you were looking into the bracing technology and trying to get a deeper understanding of this, what's happening in the aluminium flux-free bracing technology when you break this protective layer. And to understand that properly, you really need to understand the very high atomic level what's happening in the chemistry and in the structure in these layers. And you can do this type of experiments at the Hippie station. Other techniques, I mean, we have many of these XPS techniques. We have a very interesting beamline MAX IV, and we have people here in the room who knows a lot more about that than me, but here you can, it's a combined electron microscope, so you can look at the surface and you hit the surface with the X-rays and you get electrons out, and you can use that to image materials. But what I do want to talk more about is some things that we don't have today, but we will have in the soon future, which are some of these imaging techniques. And here's, for example, an experiment performed at the Swiss light source, the Tomcat beamline. And this gives an idea of how an experiment can be set up. So here we have this, we want to understand the cracking of an aluminium profile here. So the profile is put here in the chamber. You shoot it with X-rays, and you have a detector here. And why do you want to rotate it? It's because you want to do this tomographic imaging. You want the 3D structure. And if you know from in the hospital when you get your magnet or the CT scan, then you have a detector and an electron source rotating around the body. Here we have a very stable, non-rotatable X-ray source, so we have to rotate the sample instead. And if you rotate the sample really fast and very stable, you can get several of these full 3D sets of images per second. And here you can see the crack propagation happening in 3D, and you can dive down and analyze this afterwards. And this, they call it 4D imaging, so time is the fourth dimension here. It's really been pushed at these synchrotrons, and now the speed limit is somewhere up at, I think, 200 images per second. So I was at an experiment also here at Tomcat, where we were looking at foaming, or aluminium foaming technology, and they're really looking into that when it's happening live. And here's another aluminium foam experiment. It's a little bit older. And this is a 2D experiment, so it's a high-speed radiography, so 10,000 frames per second. So this is a liquid aluminium melt, and you have an injector here. You see the gas bubbles coming out. And then we're looking into understanding this when you change the different pressure conditions, how you get the different bubble sizes here, because you want to be able to control that very precisely in small bubbles to be able to build these really thin profiles with small bubble sizes, you can say. And all of these technologies, X-ray technologies, are available in lab scale, and you can do tomography in the lab scale. But if you want this really high resolution, maybe you want to rotate your sample over 24 hours and collect the data. But here with the X-rays, so bright, so many photons per second, you can get all the information in a fraction of a second. So you can start to think about different technologies and different techniques, and you don't just study matter, you study processes. And that's really the key, why you want to come to a large-scale facility like this, is when you're not just interested in understanding the properties of the matter, but also understanding the process. How do we work with industrial users? Well, we work in different ways, but one way is reaching out and talking about what is possible and making companies understand that the facility is open also for them, but talking a lot about how it's open. If you come to a facility, you come with a problem or challenge or something that you want to understand better. And in the end, you want to be able to, of course, move forward. And you see the experiment is the piece of the puzzle here in the middle. And at MAX IV, we have the stuff to help you performing in your experiment and get the most out of it. But before you get here, you also need to do some work. You need to be able to transfer your problem into an experiment. Maybe you need to develop this stage where you can rotate something and pull at it, and maybe you want a high temperature or gas stream or something. And we have a lot of experimental setups at MAX IV, but maybe not exactly yours. And after the experiment, you end up with sometimes tons of data, and you need to be able to analyze that. And maybe do some modeling and get meaningful information out of that. So a key to having success when you come here is to understand how to put this whole puzzle together. Because MAX IV, we are not staffed up to help you, especially not so much with this one. Maybe did a little bit with this one, but in our staff, after we had you visiting us, we have the next user coming to us as well that we need to serve. So we have limited resources to put into that. So how do we tackle that challenge? Well, we have two different access modes. The major access mode is that you apply for beam time and you have open calls twice per year. You describe your experiment, what you want to get out of it, and it will be ranked by some independent committee, and you get the access for free. And what you need to pay back with is that you need to publish your results in the end, in some one way or another. And then we have the other access mode, where you can buy access, and that is if you're not interested in sharing your results. And then we can set up an agreement, we have standard agreements, and you can come and perform your experiment. And this is a bit of a cluttered slide, but I want to walk you through it. There are a few companies that has some in-house knowledge. They have their staff. Maybe they can put your logo type up there as well, if you're okay with it. Yeah. That are staffed up to come to the facility, perform the experiments, and go back with the data. But there are not so many companies doing that. Many need some sort of support, and there is different organizations and companies that do so. And we are working with some small companies here in the region, working with RISE and Sverige. Wow, I need a Sverige logo type as well, I think. Yeah, we have some Sverige people here to support companies in especially these two pieces of the puzzle that we don't have. And a very important part is this one, the academic collaboration. So the broad way into the facilities for companies is through their academic collaborations. And if you just look at the numbers, here we're talking about 1-2% of the time at the facility is paid access. But these industrial academic collaborations, they're more like 20 to 40% of all the academic work that is performed there has some sort of industrial link. So that is a very important part. I just want to shortly mention that you can make these investments also, and the forestry industry is one industry that are really taking some steps. So a constellation of 8 big forest companies together with academia have this research platform, and through that they're investing in one of these beam lines, MAX Forest. And through that they're also having this portal where they are getting support for their researchers to really make the most out of this facility. But you don't need to build a beam line for 200 million. You can access in other ways. We have some strategic innovation programs here, but we've been talking to LIGHTer, and we have a PhD group visiting us. But another one is the metallic materials, and we have some people here in the room who are been taking part of these workshops that Professor Dmytro Orlov started, the Build to Gain project, and where researchers from academia, from institute, from companies and from facilities meet and talk about these challenges, the possibilities, and take these small steps to get to know each other's different challenges and opportunities, and then start to generate projects. And we are working on something called Metal Beams, which is a platform for metal industry in a very wide range. I mean, we have Alfa Laval and Tetra Pak and other companies also part of it. But here we had a workshop in connection with the Metallic Materials Strategic Innovation Program yearly meeting, where we really trying to map what are these interesting things that the industry would like to look at, to be able to see and understand, and how can we meet that, and then start to run projects, maybe develop some of these environments that are needed, and start running some test experiments. And we're really trying to work in this network that we're flowing with industry, institute, academia, and really meet up in that way. Yeah, we have some of the RISE and Spherium experts, and we have two of them here, Torbjörn and Konstantin. And Torbjörn gave an excellent talk yesterday about additive manufacturing, which is another interesting area that you can use these tools to really understand what is happening, because a lot is happening in that area. But just want to say thank you, and if you have more questions, contact me or my colleague to understand more about how you can use the facilities.
A bit late, but maybe question from Magnus?
I will be available over lunch.
We have
Okay.
do you have any other applications or investigations for lightweight in
Success stories.
Yeah.
Let me get back to you now.
Okay. Okay, in this case, Paul, maybe we should have another 10 minutes, yeah. Not longer. Not longer. Okay.
So copy again.
Copy again.
speaker. It's Peter Benson, who I personally know very well. And Peter is representing Svenskt Aluminium, Swedish Aluminium, and we talk about lightweight material challenges for Swedish industry.
Thank you very much. First of all, I'd like to extend gratitude for Swedish Aluminium for being able to be here today, and to say a few words regarding the challenges for Swedish industry. Swedish Aluminium is a business or a branch organization which is financed by members. It has 5 big members, which include Gränges, Hydro, Profilgruppen, Stena, and Kubal, which is the only smelter in Sweden. But we also have a number of smaller members that work with fabrication processes and manufacturing.
Magnus, har du kvar den här? Ja. Nej, det har jag inte. Nej. Jag drog ut den och la den vid sidan om bara. Okay, we're using it.
Yeah, that's okay. What's going to this one here? Okay. I'd like to say a few words first about light metals, sustainability, how that comes in, today's and tomorrow's vehicles, education and research, and future opportunities and challenges, all from our business or branch organization's perspective. We've heard a lot of very interesting technology today. This won't be of that depth. First of all, light metals, one normally thinks about aluminium, magnesium, lithium, and titanium. Aluminium is by far the largest in volume, with a production of around 60 million tons per year. Magnesium, as we heard, is also, besides being used as a metal element, is also used in components, and there are a number of interesting fabrication technologies like casting, thick molding, and actually the sheet production. I think that was very interesting. I was not aware of that. Lithium is mostly it's used in the batteries, of course, but also in alloy element. It was you can find aluminium lithium alloys for the aviation industry, and also titanium, which is the heaviest of these, but still a light metal. And I guess in some ways you could count very high strength steels also as a light material. About 8% of the Earth's crust contains aluminium, or consists of aluminium, so it's an abundant material. And it has unique properties. It forms in the atmosphere. It forms an oxide film, which is very dense and it prohibits further oxidation, so it's corrosion resistant. It's easy to form. It's very light, 2.7 in density. It has excellent conductivity of both heat and electricity. It's energy intensive to produce, about 13 kilowatt hours per kilo, but only 5% of that is needed in the recycling stage. Typical products or aluminium is typically used or produced as extrusions. It's like squeezing toothpaste, or in rolling, which Torbjörn talked about earlier, and in casting. And we see this in some of the products, like in car chassis. You find extrusions in certain frames, in forward and the side beams, things like that. Rolled material in heat exchanger, and cast products like the engine block. The production
Aluminium is a fairly new material. It's about 100, commercially available for about 120 years. And if we look at the growth from the 50s, there's been I would say, an amazing growth, which was sort of gradual up to the 90s, and when the 90s came, it really took off. And a lot of this is due to the development in China. We see Europe and the US have a more gradual growth, and in the US it's actually reduced. And this represents the rest of the world, and that would be the Gulf states, for example, and Russia. Sustainability covers different areas. What I want to show here is that from the beginning, most aluminum or primary plants were placed close to hydropower. So this is a way of exporting energy. This is you see this in Norway, for example, in France, in Switzerland, in Canada, in the US. But with the big growth of aluminum production, it's the energy comes from other forms, like coal and oil. But in the future, we hope to see more energy used from solar and wind parks. It's a circular material. So once you have the primary state, which includes the mining, the production of alumina, and the production of primary aluminium, which is at this stage of cast into billets or slabs, it enters production. And this is where we start to produce other components as rolled products, extrusions, and cast products. Once it goes through the lifetime, it's recycled. And this is an important step, because in the recycling, if you can retain the purity, if you can sort the metal, it's easy to use for the same application again. So if you can keep the alloys, sort them by alloys, for example, you can reuse it in the same product. I think if, for example, very high-strength steels, on the second time round, it's not possible to produce the same kind of steel. You get a reduction or a degradation in that way. So this is important. It's important to. This part is very important regarding sustainability and recycling. If we look to vehicles today, let's start with internal combustion engine vehicles like this Jaguar XJ. There's a lot of aluminum in this. The body in white, the chassis, and also in the engines you find, or in the powertrain, the engine block is made of cast aluminium. You find extruded and forged and different parts. And this is driven by weight savings. In order to, the more things you put into the car, the more weight you want to save. It's due to emissions and also to for handling and driving pleasure. But this is represents the car today. This is another car today, the Tesla Model S, which also has an all-aluminum body and chassis. The difference is here, where we have instead of the powertrain we saw before with the combustion engine, we have a huge battery and a frame. We have an electric motor. We have some suspension, of course, and wheels, which are quite similar. But this represents a big change in the products that are coming. Tesla has one alternative. Renault has one, etc., etc. All the different companies, they have their own versions of this. And it's like Torbjörn said, this is just the beginning, and we don't know which technique or which solution is going to be best, or if there's going to be several that are best. So it's sort of in an initial position. If we look closer into the electric cars, we see this. Besides the batteries, you have the housings, you have cooling and heating, you have the junction box for power electronics. These are all applications suitable for and where aluminium is used. Just looking at a battery in more depth, you have, as we previously mentioned, this foil, aluminium foil in the cells and in the modules. There's sheet products which covers that done in aluminium. Junction boxes, which are typically cast aluminium. You have different cooling systems. In this case, extrusions and tubes. Protection covers, the battery frame, which could typically be extruded, and also the crash structure, which is also typically extruded. So there's a lot of aluminium going into new products. And I heard that Volkswagen signed on an extruder for 100,000 tons of aluminium over 10 years. For battery box applications. It's a huge market. If we look to vehicles of the future, Toyota Mirai, that's the fuel cell car, and that will probably have, we don't know where the fuel cell will take off. Will this be a killer application, or will the EVs be the dominant? If we look to distribution centers for hydrogen today, there are very few stations, and it's, even though they're building, it's still quite restricted in numbers. Autonomous driving is being discussed a lot, and prototypes or cars like this are showing up at this trade shows, where it's no longer something you sit and drive. You call it, you jump in, and maybe you work, or you watch a movie, or you have a conference with colleagues or customers. So this is quite exciting, and I think if you look to younger people, they're not interested in buying cars. I used to have a Volkswagen, like the one that was shown earlier today, which was a very nice car, and it felt good to buy a car. But the younger generations, they look at their telephones, and they call their car and they jump in. They don't want more to hassle of buying it. We're seeing versions of trucks as well, like Swedish Einride, which I believe has doing test runs in the US and even in Sweden. And here Scania's NXT, which is also a concept vehicle where you could change the body depending on the application. So you use the driveline for different purposes. You could change to a bus like here, or you can swap it for a garbage truck or a distribution truck. So we're seeing a lot of these things coming on the market or coming out as well. It's very difficult to understand where will all this go. But one thing's for sure, lightweight will always be interesting. There will always be a need for lightweight solutions. If we look at the content of aluminium in cars today, the average car has about 179 kilos of aluminium. But in many of the top-end cars, we see that there's a much higher content, ranging from 511 for the Porsche Panamera to 804 kilos for the Audi e-tron. But we also see these are very expensive cars, all of them. And that's probably the easiest place to get the lightweighting in. It's also where it's probably most needed because of the added products that go into these things. Looking at the aluminum content in the future, in the coming 5 years, there's a forecast saying that there'll be an increase of 19.6 kilos of aluminium per vehicle added on to the NIBE we saw. And this will go into to battery boxes, closures, electric housings, chassis, body structures, wheels, etc. And it will be removed from the engines and transmissions of ICEs. So opportunities. In a situation where the market is changing, there will always be opportunities for new products and for new services. And a marketplace for innovation. Innovation could come in comes often in smaller companies, and sometimes in big as well. But it's definitely an opportunity now when there's so much change going on. There's also an opportunity of taking a leading position in sustainability, and with this, I mean, it will be with the reduction of engine blocks. You have a large portion of secondary material, because once you go around the wheel with the lifetime of aluminium, if it's not carefully sorted out, so you can reuse it in the same product as the beginning, then it gets then it goes into casting. That's typically what happens. And in this case, you accumulate oxides and alloying elements, which means it can't be used for extrusions with high surfaces or sheet for heat exchangers and so forth, or at least not to a large extent. So there's an opportunity here to do something with the metals. Also, it's important from a business point of view, to attract young, curious talents to the industry. And as we see, it will be a growing industry, which should also be able to attract talents. But this depends on how well we can market ourselves against them. Also, it's important to take advantage of innovations and see the facilities and the environments that are present today. This is a very interesting case, that there are incubators that can help innovators to develop their ideas and products. The challenges for the industry, many of the companies, besides the big ones of course, but our members are smaller companies, and for them I think a challenge would be to keep up with change. They have their products and they do slightly small changes from year to year, but to enter into this phase and keep up with what's going on, I think that's going to be a challenge. Again, sustainability in the environment. We have to find ways of taking care of the material, or put it this way, the secondary material is much more environmentally friendly than the middle going first time around. Again, we have to compete with all other industries to get the talents. Another challenge is the increasing knowledge of light metals. Steel, concrete, wood are taught at the universities and high schools. There's very, very little in the curriculums that are about light metals. There's some about aluminium. I believe there's more or less nothing about magnesium. and or titanium, or at least very well. So this is an important point, how to increase knowledge. Also to pick up creativity and ideas from schools and universities, and to support innovators and entrepreneurs. When it comes to education and research, there's a need for education, time and material regarding light metals. There's been a number of pushes during the years. There was a program called Talat at the end of the 90s, which was a huge, very big and very good educational package for aluminium, and was distributed to the universities. There's also a need for more research regarding light metals. Not many of the alloys used today are standard alloys from a long time ago. So that has to market demands lighter, stronger, more ductile, so that will have to come from research. There are some educational materials available today through Swedish Aluminium, and there is research support through Vinnova's SIP, metallic materials, which has a number of steps on the agenda. So for more information, please contact Svenskt Aluminium och Metalliska Material. Thank you very much.
Yeah. Running out of time a little bit here, but maybe any questions to Peter? I maybe have not a question, but as an aluminium person, I have to mention a little bit about this saying here for Peter, that actually aluminium is a little bit of transforming energy into a metal, especially for aluminium. And in our industry, that's kind of the biggest challenge we have right now. It's an energy-intensive industry. And here we are Gränges working quite a lot with this. We see the challenge of the carbon footprint. And you mentioned China. I've been to China, of course, living there for a long time. I like China. One thing I don't like in a way is the fact that China has 50% of the global production of aluminium, around 30 million tons. And if I compare the carbon footprint from our operation, the aluminium we're producing in China with Sweden, it's around 25 kilo CO2 per kilo aluminium in China, while I have here in Sweden around 4 to 6 kilo, due to the fact that we're here using different type of energy, highly power-based, mostly compared to China, which is coal power-based. I think that's the thing we are working very much here right now in the aluminium industry to really educate the industry about this part, which I think is essential. We are running out of time now. Yeah, I see that. Okay, let's go ahead then with the next and the last presentation. I think Hans-Göran Künkel from NIBE. Now we will have an interesting presentation.
Yeah, I hope so.
Thanks.
So my name is Hans-Göran Künkel. I represent NIBE. NIBE has three business areas, and I work with NIBE Element, and we do electrical heating elements of various forms. And Backer in Sösdala is the headquarters for the business area on NIBE Element. I actually brought one of the elements I will touch upon in the presentation, so you can circulate that. Maybe it helps keep you awake. Let's see, where do I push? No? No. So we're, NIBE Element is about 60 companies, close to 10,000 employees. And we do intelligent heating and control. So you can see a lot of brands that together form NIBE Element. Before I run into some of our challenges, I'll just bring you through a few examples of products. So we do a lot of products for industry, for projects like where's the point? So for more or less heavy industry, here are for plastic molding. We also do a lot of resistors. The heating element essentially is a resistor. So we do a lot of resistors for this example for wind power, a dump resistor. We do brake resistors, also for the automotive industry. We do heating products for medtech industry, used for premature born babies. We do, of course, for heating. So heating airplanes. We have nearly half of the market for heated outer mirrors on cars. And of course, white goods maybe is the first you come to think of. So we do a lot of heating products for both for the commercial white goods and for home appliances. And to close up to today's topics, we do for domestic heating. Nearly half of the production in Sösdalen in our factory is aluminum elements like the one that is circulated. Just before we pop into some more challenges, a brief on the heating element as such. So as I said, it's essentially a resistor, and there is a resisting wire in the center of the element, and there is a connection bolt that makes it possible to connect it. There is another sheath. In this case, it's aluminum. In many other heating elements, it's often stainless steel. And then it's filled with magnesium oxide. Getting back to Dmytro's favorite topic. So it's filled with magnesium oxide to keep the resistance wire nicely in the middle. And magnesium oxide is not electrically, it's electrically insulating, but it transfers the heat quite well. So that's very good. Unfortunately, magnesium oxide is hygroscopic, so it attracts moisture, which is less good, and therefore you have to close the end of seal the ends of the elements. And that is done with different, often polymers, for example, but in the aluminum case, there's a circulating. It's actually a silicon plug. They also have what we call a curve, which is there to prolong the way for for the electricity to short circuit, so that it doesn't short circuit. And in the example that is circulated, those two together are a silicon plug that are pressed into the end of the element. And aluminum element, stainless steel elements, and this is one of our big products as well. Is for water heating, for hot tub water in homes. If you look through, this is with ordinary X-ray, nothing more special, but still. So you will see the resistance wire, it's coiled, and then while you fill it with magnesium oxide, you pull it apart a bit so that the coils are separated. And you see that even if you bend the elements, so the magnesium oxide helps keep it nicely in the middle. And yeah, I forgot to say, the element is rolled. So the final thing when you produce it is that you reduce the diameter by some 15%, so that the magnesium oxide is compacted inside. And then you can bend it like this. Just a few of the challenges we face And maybe I should say that so far we're on top of them, but competition tends to tighten challenges and push them further. So there is always an end to where you get. So the panel that has been circulating is we're making that in pretty high volumes, and it goes into a radiator that you can see on the walls. And we don't have many of them in Sweden. We export a lot of them to countries where maybe you have much nuclear power and much electricity, and you use that direct electricity for heating. So our challenge in this case is the temperature. So they are getting pretty hot when inside, and touching onto a temperature where the aluminum starts to soften a bit. Of course, a bit depending on what alloy you use, but then we're under very high cost pressure. So there's a limit to how fancy alloys you can use. Also, actually, we're managing the life length test that customer wants to perform. So they run it at 15% over voltage to see how hot it gets, and then the life length test is done on 400 volts, and it is a 230 volt element. To that temperature, then there is a fan to take it 100 degrees down, and then on again to the next. And you do 50,000 cycles. Then eventually, actually, what happens is that it moves so that the element channel eventually breaks. But we're still on top of the 50,000 cycles, although just. And we see that to save money, the customer would like to make the element even a bit shorter, smaller, to save materials and raise the temperature. Well, it's where it starts getting difficult. When manufacturing the two wings, maybe you noticed that the panel consists of two wings that are pressed together in the middle. So when manufacturing these, so as I mentioned, they are rolled to compress the magnesium oxide, and so there is a contradiction, you could say, between kind of the rollability and the heat transfer properties. So you'd like to make what should I say? The ring and the wing, you would like to make a very smooth transition between them. And but if you do too smooth, there aren't any place for the rolls, which I try to illustrate to roll it and compact it, or you have to make the rolls so small or so tiny that they break. So you can't make the wing ideal in heat transfer, because then you can't roll it. So that is also a challenge. And then as well, making it thinner, taking off any kind of zigzags or to make it stronger. Of course, reduces the amount of material and makes it cheaper. But then you meet the limit when it takes too long to extrude it, so that the extrusion will be so expensive that the loss of material doesn't help anymore. So that too is well, we are on kind of a limit. And there's of course always technologies, but then again the cost pressure is very, very high on a volume product like that. And finally, another challenge that we are facing is that we want to enable. So there are some of our customers that want to make the panel look nice from start, so you don't have to build it into a radiator. You can see panels like that, maybe when in doors, entering shops, or they sit in the roof and heat from above. And to make them look nice, you want to enable them. And the process of enabling itself risks bending the panel so that you can't fill it with magnesium oxide and put it through our machinery afterwards. So we believe we're on top of that too, or getting, but there is always a challenge between producing to the cost the customer wants to pay, and we're still satisfying the customer's wishes on niceliness or effectiveness or both. So that was essentially my presentation. You'd find us and me in various places on the internet. Thank you.
Thank you very much. Maybe we shall save the question to, since we are a little bit late.
One question.
One question.
We have one.
Do we have any question? Okay. Okay. Then I don't know, Carl or Lars, do you want to say something? Maybe I just really appreciate this morning time we have had it together. I hope you did the same. Really. It's really interesting to hear this various types of presentation. And thank you, Carl, and thank you, Lars, and the Material Business Center here in Innovation School. It's a very nice region. Thank you.
And thanks to you, Torbjörn, and the rest of the presenters and all the attendees for coming. But it's not over, because now we will together go down and have lunch together. Down at the restaurant in Spira, and then up one stairs at the balcony, or what it's called. So thank you so much for now. See you at lunch.